Hi, so I will be doing problem 67 in chapter 18. So 18.67. Okay, so first of all, we know that the magnitude of the magnetic field at a perpendicular distance r from the center of a wire is B is equal to mu naught over 4 pi times 2I over r, right? And so using the given data, we can say that according to the situation of the problem, in order to calculate the maximum magnitude, that B1, which is the magnetic field given by the first wire of current I1, is mu naught over 4 pi times 2I1 over R1 for the radius of the first wire, right? So then we know that the distance from the center of the first wire to the location R1 is equal to R1 is R plus D over 2. In that same way, using that same reasoning, we can say that the magnitude of the magnetic field due to the second wire, B2, is equal to mu naught over 4 pi times 2I2 over R2, where R2 is R minus D over 2, right? So then we know that the direction of the current I2 is opposite the direction of the current I1, so that the wires will produce the opposite magnetic field. And according to the right-hand rule, we know that the direction of B1 is out of the page, and B2 is into the page. Oops. Okay. And then we also know that the magnitude of B2 is greater than the magnitude of B1. So we know that B net is equal to B2 minus B1. So it's equal to mu naught over 4 pi times 2I times 1 over R plus D over 2, or sorry, minus D over 2, minus 1 over R plus D over 2. So we know that that's B net, because I1 is equal to I2, so that way we can just say 2I instead of having to write I1 plus I2. And also we know that R is much greater than S, so we also know that this, which when simplified is equal to R squared minus D over 2 squared, so we know that this is approximately equal to R squared. Therefore, B net is approximately equal to mu naught over 4 pi times 2I D over R squared. So if we substitute in all the values for this equation, they're all given to us, we essentially get that B net is equal to 1e negative 7 times 2 times 15 times 3e negative 3 all over 5e negative 3 meters, right? And that is equal to 3.6 e negative 8 teslas. So that is part 1. So if we want to do part 2, so we know that the two wires are twisted like this. So let's say this is I1, and this is I2. So the current direction in the first wire is opposite to the current direction in the second wire, right? And then in that same way, we know that the magnetic field contributions by region where wire 1 is nearly canceled by the regions where wire 2 is closer. So the magnetic field is minimized rather than maximized. So that's part 2. And then for part C, we want to find for two long parallel wires like those shown in part A, a distance d apart and carrying conventional current I in opposite directions, find an algebraic formula for the magnetic field. A perpendicular distance r is much greater than d to the right of the wires. So we know that since the wires are so long, and the magnetic field of B1, once again, is equal to mu naught over 4 pi times 2I1 over R1. And then B2 is equal to mu naught over 4 pi times 2I2 over R2, where R1 is R plus D over 2, and then R2 is R minus D over 2, right? And we also know that the direction of the current I2 is opposite the direction of the current I1. So we're essentially doing the same thing that we did in part 1 again. So we're saying that B net is equal to B2 minus B1, which is equal to mu naught over 4 pi times 2I times 1 over R minus D over 2 minus 1 over R plus D over 2, right? And so since we can simplify this further, we will do so. We will simplify that down to S over R squared minus D over 2 squared, so that our new B net formula is mu naught over 4 pi times 2I times S over R squared minus D over 2 squared.